All right, so the second chapter, Intro, deals with early atomic experiments, at least in the beginning portion, and it's a useful thing for us to take a look at. We're not going to dedicate a lot of class time to it because it does fall under just broad history. But, late 1700s, the end of the 18th century, we had Antoine Lavoisier. And one of the things that he observed is that if we had the masses of two things going into a chemical reaction, the product of that reaction had the same mass as the things that went into it. And that led him to believe that there was a conservation of mass law at hand. So the things that went into a reaction also came out of a reaction, although differently, but they weighed the same. So law of conservation of mass is credited to Antoine Lavoisier, who was later beheaded as part of the French Revolution. Not a great time for him. Now John Dalton, was an American, a Quaker, colorblind, and had a lot of great ideas on a lot of different things, but one of the things that he is credited for is a general atomic theory that sort of led thought for the next part of the scientific exploration. And one of the first things in there is it said that every element is composed of a tiny indestructible particle, and they called them atoms. People have been kicking around the term atoms before, meaning indivisible, and he believed that elements were composed of those tiny things, and that you couldn't get any smaller. Now, this was actually a really unique concept because it's hard to understand that you can believe in something that is too small to see, but really there. So all atoms of any given element have the same mass, and their properties distinguish them from other atoms of other elements, meaning that atoms of one element are not the same as atoms of another element. And there are only so many elements, and their atoms are all unique from each other. So that, again, was another really neat idea. The third is that the atoms will combine in simple whole number ratios, and they'll form molecules. So he knew that there were things like water that was not necessarily atomic, but there were atoms in water, and the proportions in which they combined, they can be defined by simple whole number ratios. And then atoms of an element cannot change into atoms of another element. In a chemical reaction, they only change the way that they are bound together with other atoms. So that is very, very true, although not universally true. This leaves out nuclear reactions, but this is something that he did not know about at the time. Still, this is a very important guiding thought at the time because we had lots of people doing different kinds of reactions, and they really needed to understand that a little bit of lead did not turn into gold, and that was something that people, alchemists were promising. So something a little more fundamental was cathode rays, and J.J. Thomson is credited with doing some of the work that was here. And in his experiment with cathode rays, what he had was this partially evacuated tube. So there is a kind of a vacuum in here. There's metal on this side, metal on that side. And then he ran a high voltage across it so that one side became negative, the other side became positive. And what he noticed is that there was always a beam that would travel in a straight line from the negative end to the positive end. And because that would end up happening, he knew that there was some sort of fundamental particle at play there. And this was the discovery of the electron. So what he was able to do was measure the charge to mass ratio of that species. So what he did is that he sort of changed his setup. He put a powerful magnet here because one of the things he knew is he could deflect that beam with a magnet. And he measured the charge to mass ratio, which was negative 1.76 times 10 to the 8th. And that ratio is about 2,000 times less than that of hydrogen. So whatever elementary particle this was, it was incredibly light. And one of the things that he remarked upon closing this out was that there is a new phase of matter from which all chemical elements are built up, meaning that this thing that he found, the electron, not knowing exactly what it was, is something that's found in all atoms and in all elements. So it was sort of a very revolutionary thing. Now, another guy, Robert Millikan, working at the University of Chicago, took that information and then ran with it. And so what he did is what's known as the famous oil drop experiment. And so he was able to determine the charge of a single electron by taking some oil, squirting it into a chamber. There's a small hole at the top of this chamber, and particles of oil would fall through. And here they had an ionizing radiation. And so this area was flooded with sort of like a negative charge, and these oil droplets would pick up a negative charge. And then there's a plate here and a plate here, and they had different charges. So there's a negative charge in this bottom plate and a positive charge in this top plate. And so he could actually make these things levitate. And depending on the size of those particles, he would guess that there was some whole number of negative charges built up on there, negative electrons on there. And by integrating over these, he was able to figure out the charge of just one electron, which turned out to be negative 1.6 times 10 to the minus 19 coulombs. And then using the charge to mass ratio that Thomson found, he got the mass to be 9.10 times 10 to the minus 28. Now that's amazing because there's no scale on the planet that can measure something this small. Right? He was able to do it early 1900s, largely using very available things and math. So that's kind of a really cool thing. Now, this was done at the University of Chicago, and you can and a lot of this stuff is preserved there, so you can see the remnants of these historic experiments. And for this, he won the Nobel Prize in Physics in 1923. Now we have Rutherford, another one that's sort of familiar. So you've got some source here, some which would emit particles, alpha particles. And what he was expecting, based on Thomson's results, is you've got some soup of electrons, and then some, some randomly dispersed positive charges. And Rutherford was interested in measuring these small angles at which some of these particles would scatter when they go through gold foil. Turns out there is a lot of small angle scattering, but there's some non-ignorable large angle scattering, and some very large angle scattering. So what was causing that? So this model that he thought he was working on turned out to be a false model, and instead came to understand that there was some very small dense nucleus in the center of an atom through which these alpha particles could not pass, and they would be deflected at large and small angles as a result. So what he was able to determine is that most of the atom's mass and all of its positive charge was contained in the nucleus, and that most of the volume of its atom is empty space, and that there are many negatively charged particles, are as many negatively charged particles as there are positively charged particles in a neutral atom. And so he gave us the most complete picture of an atom through a relatively simple experiment. Now, he got the Nobel Prize in 1908, not for this work per se, but for work that he was doing in basic atomic work, which had a lot to do with radioactivity and disintegration of other atoms. So this was really a really interesting time, because we went in a relatively short period of time, 100 years of human history, going from I wonder if everything is made of something to we know exactly what it's made of. It's made of atoms. And that is a really big leap. Okay?